directional derivatives and the gradient vector. First, let's understand the concept of a directional derivative. If I have some point P prime in the xy plane, when I plug that point, which has coordinates x0, y0, into the function f, I get the point P, which has coordinates x0, y0, z0. What I want to do is take a look at the tangent line to P, but understand that we can draw infinitely many tangent lines to the surface at the point P. So what we're doing is we're taking the tangent line that points in the same direction as some given vector u, which is down here in the xy plane. Now for simplicity, we will define this vector u to be some unit vector, so it has to have a length equal to 1. And we're looking at the slope of this tangent line, which points in the same direction as u. Now this slope is what we call the directional derivative of the function f at the point x0, y0 in the direction of the vector u. And it has the following definition. Now let's understand where this definition comes from. So if I graph my point P prime, which has coordinates x0, y0 in the xy plane, we can see that P prime would be a point right about here. So again, this is our x-axis, this is our y-axis, here is P prime. And I want to look at the vector that goes from P prime to Q prime. Now Q prime is some other point that's going to be on your function here. Well, Q prime is the point in the xy plane, and when you plug those numbers into the function, you get the point Q. So Q prime is over here, let's say, and I'm looking at the vector P prime, Q prime. Now we can see that the vector P prime, Q prime points in the same direction as u, but it's not necessarily the same length as u. So we can express P prime, Q prime in terms of u. And we can do this by just realizing that the vector P prime, Q prime has coordinates x minus x0 and y minus y0. And the vector u has coordinates a, b. Now understand that since the vector u and the vector P prime, Q prime point in the same direction, that means we can express these vectors in terms of each other. Namely, we can say that the vector P prime, Q prime is equal to some multiple of the vector u. So I'm going to say that it's equal to h times u. But this means the vector x minus x0, y minus y0 is equal to the vector h times ab. And if I simplify here, we get the vector x minus x0, y minus y0 is equal to the vector ha, hb. But that means that x minus x0 would have to be equal to h times a, and y minus y0 would have to be equal to h times b. And if we solve for x and y, we can see that x would be equal to x0 plus h times a, and y is equal to y0 plus h times b. And that allows us to rewrite the coordinates for q prime. So instead of calling it xy and 0, we can call it x0 plus ha, y0 plus hb, and 0. So now to find the slope of the tangent line through the point P up here on the curve, and we know that it is pointing in the same direction as u down here, what I'm going to do is find the slope of the secant line, which goes through points P and Q up here on the curve. And if I can find that slope, I simply need to take the limit as the point Q gets closer and closer to the point P, And then the limit of the slope of that secant line will become the slope of the tangent line. So now, what are the coordinates of Q? Well, we can see here that Q has coordinates x, y, and z. And those coincide with the coordinates down here, except that down here the z coordinate is 0 because it lives in the xy plane. And up here you have whatever coordinate z is that is on the function there. So the coordinates for Q can be rewritten like we wrote the coordinates for Q prime. So here are those coordinates for the point Q. Now to find the slope between P and Q, what I need to do is take the difference of the z values and divide them by h. Well, the z values are going to be the function value of x naught plus h times a, and then the function value of y naught plus h times b. So in other words, we have to plug both of these values into the function, and that's going to produce a single function value, minus the function value at the point x naught, y naught, which is point Q. And then we divide that by h, which is the distance between these 2 points, the horizontal distance between those 2 points. And this will give us the slope of the tangent line. So long story short, the directional derivative is the slope of the tangent line to the surface in the direction of some given unit vector u. And it's important for u to be a unit vector. That allows us to very easily define h down here. So now we need an easy way to compute the directional derivative. So we have the following theorem to help us with that. So if f is a differentiable function of x and y, then f has a directional derivative in the direction of any vector u, unit vector, that is, and it is given by the formula partial derivative of f with respect to x multiplied by the first component of that unit vector plus the partial derivative of f with respect to y multiplied by the second component of that unit vector. This is an extraordinarily easy formula for finding the directional derivative. So let's take a look at the following example. Find the directional derivative of the function at the given point in the direction of the given vector v. Now, first of all, to find the directional derivative, we need to have a unit vector. So if the vector v is the vector 3, 5, we need to normalize this vector by finding its length and dividing by that length. So the magnitude of v, of course, is the square root of 3 squared plus 5 squared. This is the square root of 9 plus 25, which is the square root of 34. So if I transform the vector v into a unit vector that points in the same direction as v, this is going to be the vector 3 divided by radical 34 and 5 divided by radical 34. So now what I need are the partial derivatives. So the partial derivative of f with respect to x, let's think about how to do this. Notice that you have a quotient here, and you have an x in the top and the bottom. So we're going to use the quotient rule to find this derivative. We will treat y like a constant. So the derivative of a quotient, we take the denominator, multiply it by the derivative of the numerator with respect to x, which is 1. Then we subtract the numerator, multiplied by the derivative of the denominator, so that is 2x plus 0, so it's just 2x. And then we divide that by the denominator squared. And if we do the math on this, we get y squared minus x squared divided by x squared plus y squared squared. Now let's go ahead and find the partial derivative with respect to y. Same concept, except that now we are taking the derivative with respect to y, so x is regarded as a constant. I'll go ahead and use the quotient rule, even though you don't really have to in this case. We're going to take the bottom function, denominator, multiplied by the derivative of the top function, which is 0 with respect to y, minus the top function, multiplied by the derivative of the bottom function. Derivative of x squared is 0, derivative of y squared is 2y, and then all divided by the denominator squared. And this simplifies to negative 2xy divided by x squared plus y squared squared. Now the next step is we have to evaluate our partial derivatives at the point where we want the tangent. So it's at the point 1, 2. The partial derivative with respect to x evaluated at 1, 2 is 2 squared minus 1 squared divided by 1 squared plus 2 squared quantity squared. This is 3 divided by 25. And the partial derivative of y evaluated at the point 1, 2 is negative 2 times 1 times 2 divided by 1 squared plus 2 squared quantity squared. And this is negative 4 over 25. Finally, to find the directional derivative of our function f in the direction of the unit vector that is pointing in the same direction as v. Now you could just say v down here, but I like to emphasize the fact that it needs to be a unit vector. This is going to give us the partial derivative with respect to x evaluated at the point 1, 2, which is 3 over 25. We're going to multiply that by the x coordinate of our unit vector, which is 3 over radical 34, plus the partial derivative of f with respect to y, which is negative 4 over 25, multiplied by the y coordinate of our unit vector, which is 5 over radical 34. And what you have here is 9 over 25 radical 34. Excuse me. Yes, that's right. Minus 20 over 25 radical 34, which is negative 11 over 25 radical 34. And so this is the directional derivative for this example. Let's briefly talk about how to represent a unit vector by only using an angle. Now, when I say an angle, I'm referring to an angle from the positive x-axis rotating counterclockwise. We know that if the vector u has a length of 1 unit, the x-coordinate or first coordinate of that vector will be the cosine of theta, and the y-coordinate will be the sine of theta. So a unit vector that points in the direction of theta can be represented by cosine theta, sine theta. Now let's find the directional derivative if we have the following function, and u is the unit vector in the direction given by the angle theta equals pi over 6, measured from the positive x-axis. What is the directional derivative in the direction of u at the point 1, 2? So again, let's go ahead and find our unit vector, u, which we now know is going to be the cosine of pi over 6, sine of pi over 6, which is the vector radical 3 over 2 and 1/2. Now we need the partial derivative with respect to x. This is 3x squared minus 3y, and the partial derivative with respect to y is going to be negative 3x plus 8y. Plug in the point 1, 2 and the partial derivative evaluated at 1, 2. So let's go ahead and plug in x equals 1 and y equals 2. That gives us 3 minus 6, which is negative 3. And the partial derivative with respect to y evaluated at 1, 2 is going to give us negative 3 plus 16, which is 13. And so the directional derivative of the function f in the direction of u will be negative 3 times radical 3 over 2 plus 13 times 1/2. And this is 13 minus 3 radical 3, all divided by 2. Now we define the gradient vector. If f is a function of two variables, x and y, then the gradient of f is the vector function gradient f defined by the vector where the x component is the partial derivative with respect to x, and the y component is the partial derivative with respect to y. So for example, if the function f of xy is sine of x plus e to the xy, the gradient of this function, the gradient vector of this function, is simply the vector fx fy. The derivative here with respect to x is cosine of x plus y e to the xy, and the derivative here with respect to y is x e to the xy. And if I want the gradient vector at a point, all I need to do now is plug in the value x equals 0 and x equals 1 in this case. And when I plug those in, I get the vector 2, 0. So the gradient vector in general is this vector function, and the gradient vector at a particular value for x and y is this vector. Why do we bring up the gradient vector? Well, it has a couple of uses, but one of the uses is that we can use it to easily define the directional derivative. So we know the directional derivative of a function f in the direction of u is equal to fx times a plus fy times b, where a and b are the coordinates of your unit vector u, and fx and fy are the partial derivatives. But notice that this is simply the vector fx fy dot product with the vector ab, because the definition of dot product says that this is the dot product of these two vectors. Well, this is simply the gradient of f, and we're taking the dot product of that with the unit vector u. So we can redefine now the directional derivative as the gradient of the function dot product with the unit vector u. So now that we have this new formula for finding directional derivatives, we can use it to find them. Now, there really is no advantage to this formula other than the fact that it helps you to remember the formula a little more easily. So in this example here, find the directional derivative of the following function at the point 2, negative 1, in the direction of the vector v, which is the vector 2, 5. So first, let's go ahead and find a unit vector pointing in the direction of v. So v is the vector 2, 5. The magnitude of v is the square root of 4 plus 25, which is the square root of 29. And so the unit vector in the direction of v is going to be 2 over radical 29, 5 over radical 29. Now I need to find the gradient vector, which is fx, fy. So let's find fx and fy. Fx is going to be 2xy cubed, and fy is 3x squared y squared minus 4. And then finally, we have to find the gradient vector at the point, in this case, 2, negative 1. So I need to plug in x equals 2 and y equals negative 1. So that's going to give us 2 times negative 1 to the third. And then for the y coordinate, 3 times 2 squared times negative 1 squared minus 4. And this is the vector negative 4, and then 3 times 12 times 1 minus 4 is 8. So now that I have the gradient and the vector here, all I need to do is find the dot product. So the directional derivative of the function f in the same direction as u at the point 2, negative 1 is simply going to be the gradient of f at 2, negative 1 dot product with u. And in this case, that is the vector negative 4, 8 dot product with 2 over radical 29 and 5 over radical 29. And when we do that dot product, we get negative 8 over radical 29 plus 40 over radical 29. and this is 32 over the square root of 29. If we have a function of 3 variables, we can define the directional derivative in the same way. So first, the gradient now is simply fx, fy, fz, because there are 3 variables now. And the directional derivative of your function f in the direction of u at the point xyz is the gradient at the point xyz dot product with the unit vector u. So in our next example, we have a function of 3 variables now. First, let's find the gradient of the function f, and then we'll find the directional derivative of f at the point 1, 3, 0, and in the direction of this vector v here. So for part A, let's go ahead and find the partial derivatives fx, fy, and fz. The partial derivative with respect to x is going to be 1 times the sine of yz, which is sine of yz. With respect to y, x is now a constant, and the derivative of sine of yz is going to be sine of yz times the derivative of yz, which is z. So that's going to be x times z times, oh, I said sine of yz. I meant cosine of yz, of course. Derivative of sine is cosine. There we go. And the derivative with respect to z is very similar. X is a constant. Derivative of sine is cosine of yz, and then times the derivative of yz with respect to z, which is y. And so that's going to give us xy cosine of yz. So our gradient vector is going to be sine of yz, xz cosine of yz, and xy cosine of yz. So for part B, the first thing I need to do is find the unit vector that points in the same direction as vector v. Vector v is the vector 1, 2, negative 1. So the vector u that points in the same direction is going to be 1 divided by the length of that vector. And the length of that vector is 1 squared plus 2 squared plus 1 squared, which is 6, and then the square root of that. So we have radical 6 as the length. So we're going to divide all these coordinates by radical 6. And then, of course, we need the gradient vector f, but now evaluated at the point 1, 3, 0. So we have to plug in x equals 1, y equals 3, and z equals 0 into all of these. Notice when you plug in z equals 0, that makes the first coordinate 0. And when you plug in z equals 0 here, you also get 0. And if z equals 0 here, the cosine of 0 is 1 multiplied by x and y. So multiplied by 1 and 3 is going to give you 3. So the gradient vector at the point 1, 3, 0 is the point 0, 0, 3. And now we just need to take the dot product of 0, 0, 3, and 1 over radical 6, 2 over radical 6, and negative 1 over radical 6. And when you do that dot product, we're going to get 0 plus 3 times negative 1 over radical 6, or negative 3 over radical 6. And, I mean, you can simplify this answer. You don't have to necessarily, but negative 3 over radical 6, if you did attempt to rationalize the denominator, you would get negative 3 radical 6 over 6. And then you could cancel this and get a 2 there. And so you could say negative radical 6 over 2. And in this case, that really is kind of a simpler answer, but honestly, there's not a whole lot of difference between both of those. So I would accept either one, but do that at your own risk because not all professors accept answers in that form. Now let's consider the maximum value of a directional derivative. Suppose f is a differentiable function of 2 or 3 variables. The maximum value of the directional derivative is the absolute value of the gradient of the function and it occurs when u has the same direction as the gradient vector. Okay, so let's go ahead and prove this. We know that the directional derivative of a function f in the direction of u is equal to the dot product of the gradient of the function f and the vector u. But we know that the dot product of two vectors is also equal to the length of the vector gradient of f multiplied by the length of the vector u multiplied by the cosine of theta. But we know the length of vector u is 1 because by definition u is a unit vector. So this is equal to 1, which means we can ignore it. And this becomes the magnitude or length of the gradient vector f times the cosine of theta. Now think, when will this be the largest? Well, we know that cosine has a maximum value of 1. So if I have a quantity multiplied by cosine, this is going to be its biggest when cosine is equal to 1. So we know that this is going to be the absolute value of the gradient vector. In other words, this is going to be the maximum value. I shouldn't say that these are equal. What I should say is when the cosine of theta is equal to 1, this is going to be its maximum value, which is the magnitude of the gradient vector. All right, well, when does that happen? When is the cosine of theta equal to 1? Well, that happens when theta is equal to 0 degrees or 0 radians because cosine of 0 is 1. Well, if the angle theta is 0, what that means is that these two vectors are pointing in the same direction because theta is the angle between these two vectors. So when are you going to have a maximum value? You're going to have it when the cosine of theta is 1. That happens when theta is 0, which means the vector u is pointing in the same direction as the gradient f. And what is that maximum value going to be? It's going to be the magnitude of the gradient vector. So for example, if you have a function f, let's go ahead and find the rate of change of f at the point 2, 0 in the direction from p to q. And then part B, in what direction does f have the maximum rate of change? And what is this maximum rate of change? Okay, so first of all, for part A, what we need to do is we need to find the direction vector. And they tell us that it's in the direction from P to Q. So we need the vector PQ. So to get that, I'm going to subtract coordinates. So the x-coordinate of Q is 1/2. We're going to subtract the x-coordinate of P. And then the y-coordinate of Q is 2. And we're going to subtract the y-coordinate of P. And this gives us -3/2, 2. Okay, but now we need our unit vector, which points in the same direction as PQ. So we need the magnitude of PQ. The magnitude of PQ is the square root of -3/2 squared plus 2 squared, which is the square root of 9/4 plus 4, which is the square root of 25/4, which is 5/2. So vector u, that is a unit vector and points in the same direction as PQ, is going to have the x-coordinate but divided by 5/2, and the same y-coordinate here but divided by 5/2. And this is going to give us the vector -3/5 and then +4/5. So now that we have our unit vector, let's find the gradient of f. The gradient is going to be the partial derivative of this function with respect to x. That is going to simply be e to the y. And then the partial derivative of this function with respect to y, which is going to be x e to the y. And then we need to find the gradient vector evaluated at the point P, because it does say at the point P, which is the point 2, 0. So we're going to plug in x equals 2 and y equals 0. Y equals 0 here gives us e to the 0, which is 1. And x equals 2, y equals 0 gives us 2 times 1, which is 2. And so the rate of change, or the directional derivative of f in the direction of u, is the vector 1, 2 dot product with negative 3/5, 4/5. And this is negative 3/5 plus 8/5, which is equal to 1. Now for part B, in what direction does f have the maximum rate of change? Well, the maximum rate of change occurs when you go in the direction of the gradient vector. So it has to be in the direction of the vector 1, 2. So we're just going to simply write in the direction of the vector 1, 2. And what is the maximum rate of change? Well, the maximum rate of change is the magnitude of that gradient vector. So it is the magnitude of the vector 1, 2, which is the square root of 5. Next example, suppose that the temperature at a point xyz in space is given by the following function, where T is measured in degrees Celsius and X, Y, and Z are measured in meters. In what direction does the temperature increase fastest at the point 1, 1, negative 2? And what is the maximum rate of the increase? So in what direction? Well, we know it has to be in the direction of the gradient vector at this point. So this is just a fancy way to ask you, what is the gradient vector? All right, so first of all, let's go ahead and rewrite our function t. I'm going to write it as 80 times 1 plus x squared plus 2y squared plus 3z squared to the negative 1 power. And then we need the partial derivative of t with respect to x, the partial derivative of t with respect to y, and the partial derivative of t with respect to z. And so the first one is going to give us negative 80, 1 plus x squared plus 2y squared plus 3z, that should be squared, to the negative 2, times the derivative of the inside. Now with respect to x, all these other derivatives are 0 except for this one, and so that's just going to be 2x. On to the next one, ty is going to be negative 80, same thing. And then multiplied by the derivative of the inside with respect to y, and that gives us 4y. And finally, tz, very similar. And the derivative of the inside here is going to be 6z when we do it with respect to z. Now, we need to find the value of each of these partial derivatives at the point. So I'm not going to bother simplifying. I'm just going to plug in x equals 1, y equals 1, and z equals 2. So now our gradient vector for the function t at the point 1, 1, negative 2 is going to be the vector. So we'll start with this one, plugging in x equals 1, y equals 1, and z equals negative 2. And that gives us a value of negative 160 over positive 256. So keep in mind, this is a negative 2, which means when you plug in all those numbers, you need to drop this down to the denominator and square it. And then we'll do the same thing for ty, plug in x, y, and z, and also for tz, and we should get the following values. All right, so these are not really pleasant numbers, but you can simplify these quite a bit. So let's go ahead and reduce each of these fractions. Okay, so this is what we get here. And so if we were going to tell somebody this is the direction you need to travel in, this is probably not the best vector to give for that. So what I could do, since I'm just looking for the direction of this vector, is I can turn these into whole numbers by multiplying all of these by 8 and then dividing them all by 5. And if I do that, the vector that has the same direction would be the vector -1, -2, and 6. So this is the direction that you would need to travel in if you wanted to have the maximum rate of increase. Now, what is the maximum rate of increase? Now, when I go to find the maximum rate, I have to take the magnitude of the gradient vector at that point. Okay, so I'm not allowed to use this. This is simply a simplified version to give us the direction. Okay, now if I wanted a unit vector here, I could divide this by its magnitude, which is the square root of 41. But in terms of just giving a direction, this is fine. But now what is the maximum value? It's going to be the square root of the sum of the squares of all the components of your gradient vector. And if we do the math there, we end up getting 5 radical 41 all over 8. I'll leave the math there to you, but that is what you should end up with. And by the way, an approximation here, this is approximately 4 degrees, and this would be Celsius per meter. So the maximum increase comes when you travel in this direction, and that increase is going to be 4 degrees Celsius per meter of travel. Now we can also talk about tangent planes to level surfaces. This is a little bit tricky to visualize because we are looking at essentially a function of 3 variables. And so level surfaces are not the same as level curves. So basically, we're just talking about the tangent plane to some kind of a surface. So if this surface is defined by some function, f of x, y, and z is equal to 0, then the tangent plane at the point x naught, y naught, z naught can be given by this formula. Now, I'm not going to prove this here. Instead, we're just going to use it. So let's find the equations of the tangent plane and the normal line to the ellipsoid given here. So we have an ellipsoid at a certain point. So here is the graph of that ellipsoid. The point -2, 1, -3 is down here somewhere, and we're finding the tangent plane to that point. And then also the normal line to that point that goes through that point of tangency to the plane. So first we need the partial derivatives evaluated at the point -2, 1, -3. First, we need to understand that a way of looking at this is we have a function of x, y, and z, and it is set equal to the value 3, and this is what is giving us our level surface. Now in this case, the function f of x, y, and z would be equal to the function x squared over 4 plus y squared plus z squared over 9. So the partial derivative with respect to x is going to be x over 2. Partial derivative with respect to y is 2y. And the partial derivative with respect to z is 2z over 9. And now we're going to plug in the point -2, 1, -3 into each of these partial derivatives. And in doing that, you can see that we get the following values here. The math here is pretty simple, so I'm going to leave this up to you to understand what I'm doing here. Just plugging in these values, right? And so we have now essentially the gradient vector, right? Because that's all these are when you put them together. It's just the gradient vector. -1, 2, and -2/3. And now we just need to multiply those by the quantities that you see here. So we're going to have -1 times x minus x naught. X naught is -2, plus 2 times y minus y naught. Y naught is 1, plus -2/3, multiplied by z minus z naught, and z naught is -3. And we set this equal to 0, and we get -x minus 2 plus 2y minus 2 minus 2/3 times z minus 2 is equal to 0. Or if we move stuff over to the other side and make it look a little bit nicer, I can say x minus 2y plus 2/3 z is equal to -6. And if you want, you can clear the fraction there. That's really kind of up to you. I do think it looks a little nicer if we multiply everything by 3 here. And this is the tangent plane to that level surface. Next, we want the equation of the line, which is perpendicular to that plane at that point. Now remember, the vector that you see here, the coefficients of x, y, and z in a plane, that gives you the coordinates of the normal vector, right? The perpendicular vector. So remember, your symmetric equations for a line is simply x minus the x coordinate of the point, which is x minus -2, divided by the x component of the normal vector. And of course, the normal vector to the plane is the same as the direction vector for the line. So I should say the x coordinate of the direction vector. And that's equal to y minus 1 divided by the y component. And that's equal to z minus -3 or z plus 3 divided by the z component. Now this next problem is the same thing, but it is a different type of function. Here we have z is equal to a function of x and y, whereas in the previous problem we had a function of 3 variables. To use the same method though for this problem, what I need to do is set this equal to 0. So I can say 2x squared plus y squared minus z is equal to 0. And then I can regard this function here as my function of x, y, and z. And so now to find the tangent plane, we just go through all the same things that we just did. And there's all the work. And if you want to pause the video to check what I've done, be my guest. Let's conclude the section by talking about properties of the gradient vector. So we know that if f is some differentiable function of 2 or 3 variables, and let's go ahead and suppose the gradient vector is not 0, then we know that we can define the directional derivative by using the gradient vector. We know that the gradient vector points in the direction of maximum rate of increase, and that maximum rate of increase is the magnitude of the gradient vector. One thing we haven't talked about, though, is what does the gradient vector itself look like? Well, in 2 dimensions, this is the easiest way to see it. If I have some level curve in 2 dimensions, the gradient vector at a point on that level curve will be perpendicular to the tangent line at that point. So the gradient vector always points perpendicular to the tangent line. So that is what it looks like. And it's kind of interesting because we've been talking about the gradient vector, using it in all these problems that we've done, but we never actually discussed what the gradient vector itself looks like. And so that is what it is. And that's why it's so important, because it is basically perpendicular to the level curve. And we define that by being perpendicular to the tangent. Okay, and so that's it. And that concludes this video lesson.